All right, so when I erased the last slide, what I had drawn up here was the definition of what I called a dynamic matrix. Or really, the whole thing is defined in terms of an eigenvalue problem. So I have that, some left-hand side that involves a constant times a vector. Let's think about this as a vector. Let me, even though it has two free components, let me talk about why I would call that a vector in just a second. Hold on a second. Equals basically some, what I'll call a matrix component. So this is the dynamic matrix. So again, I'm thinking of K and I together as forming a set of a vector. So K and I forms a vector of possible values, and K prime and J form another direction of that vector. So this is really sort of a matrix equation being summed. So this is a matrix summed over the free components of another vector. So this is essentially a definition of matrix multiplication, where this is the matrix equals a constant times the same vector. Okay, so that defines an eigenvalue problem. Now let me say a little bit more about, let me clear up one thing. So I said that I should think about K and I as essentially indices defining a vector. What do I mean by that? Well, essentially like K is the number of atoms in a unit cell, or it has, so it represents the atom of the unit cell. And I represents the direction of motion. So how many possible values does K have? Well, it depends on how many atoms are in the unit cell. So if you have one atom per unit cell, there's just one. And the direction of motion is always the same. There are always three possible values. But this one really depends on the number of atoms per unit cell. So, but there are, how many different ways can I rearrange these in different combinations? Well, it's just K times I. So like what I do is I think it, like, let's say that the number of atoms is 1 in the unit cell. Then how many different ways can I do this? I can do, K equal 1, I equal 1, 2, or 3. Or in other words, X, Y, and Z. Okay, what if there are 2 atoms per unit cell? So then, if there are 2 atoms per unit cell, I could do K equals 1, I equal 1, 2, and 3, or I could do K equal 2, I equal 1, 2, or 3. So in this case, there are 6 different ways that I could come up with things. So what I'll do is I'll just think about this as in a 2 atom per unit cell sense. I would think about this thing as a vector that has length 6, right? Because there's 6 different ways I could come up with a value of V, right? Depending on which of these indices are set the way they are. So that's the reason why I say that I and K together really make a vector. I can think about it as vector components if I really expand these out. And so anyway, that's the way I'm going to think about things. So there are 6 different ways I can rearrange I and K, and like on a 2 atom per unit cell thing. And this one would be also 6 different ways I can come up with K prime and J combinations. So it's really, I can really think about that as a matrix. Now, what else was I going to say? Oh yeah, I was going to say, okay, so while I'm erasing this, think about what you know about symmetric matrices. So if I look at this, this thing that's up here and how I've defined it, and I just realized that I'm missing some factors here. Remember that there was some mass stuff going on over here. So the mass of the atoms actually matters, of course, to the phonon spectrum. So I'm sorry I just caught that, but there was a mass term missing there. Okay, so if I look over here at the definition of my dynamic matrix, what I'll see is that it's symmetric. So what do we know about symmetric matrices? Well, a couple of things. In fact, this actually can be formed as a symmetric, what's called a Hermitian matrix, which means that essentially the transpose is equal to the transpose is equal to the original matrix, but only if I do a complex conjugate, or at least I can make it look that way. So what do we know about symmetric matrices? A couple of things. The main thing is that symmetric matrices have real eigenvalues. Real eigenvalues. So this is a symmetric. It's actually also a Hermitian matrix. Hermitian matrix. It's got real eigenvalues, and in fact, we'll see that they have to be positive in a second. I'll talk about that. The other thing is that they have orthogonal eigenvectors. So, based on the discussion we had about the diatomic chain, we kind of know that these eigenvectors, essentially what they represent is what the different atoms in the unit cell are doing, like what direction they go when they're associated with the solution to the eigenvalue problem. So, like we had shown before that there were particular displacement patterns that were associated with optical phonons rather than acoustic phonons. And this is how that all sort of shakes out. What we'll see is that, this is essentially an eigenvalue problem where the omega squareds are the eigenvalues. We'll be able, for any particular value of Q, you can solve for the eigenvalues, but you'll get different eigenvalues. So remember, so for example, for a 2 by 2, or for a 2 atom per unit cell thing, we're expecting this to be a 6 by 6 matrix, meaning that we're going to get 6 eigenvalues. Well, the upper 3 of those eigenvalues are going to represent optical phonons in that case, and they have one displacement pattern as opposed to acoustic phonons. The other thing is, and we'll talk about this, is that there are other solutions. So I said there's 6, not 2 now. The other ones, so the other polarizations that come out, the eigenvectors, are going to correspond to transverse phonons, meaning that, I'll have, rather than having compressive waves that basically travel in a particular direction, another possibility is that I have sort of undulating waves where the atoms individually, their displacements are up and down, but they're carrying energy in a particular direction. So literally that's what it normally means to have sort of that's called a transverse wave. And in fact, because it's in 3 dimensions, you can have, so if I have a wave that's carrying energy in this direction, I can either have compressive waves to do that, I can have a transverse wave, but I can also have transverse waves that are in and out of the page. So that'll form 3 different orthogonal eigenvectors that carry energy associated with different values of omega. So, and that happens even for a 1 atom per unit cell thing. So for a 1 atom per unit cell thing, I can have these compressive waves, I can have transverse waves of 2 different varieties, and they're orthogonal to one another. So the fact that this dynamic matrix is symmetric and Hermitian guarantees that those eigenvalues, or the frequencies that you come up with when you solve this thing, are definitely real. In fact, they're positive if you have a stable crystal structure, and they're also orthogonal to one another. A third thing, which is probably less appreciated, is that because it's symmetric and Hermitian, there's really awesome solvers. So numerically, we can actually, numerically, there are good iterative solvers. And that means that no matter how many atoms we have per unit cell and however big this thing is, there are really good numerical solvers that can iteratively solve this eigenvalue problem. Note that, if you don't have some of those nice things, you have a problem in that an eigenvalue problem is fundamentally requires the solution to a polynomial equation. And if you have a very long polynomial equation, there are multiple solutions, and getting all of those solutions numerically is a little bit expensive if you don't have some nice properties going on. But it turns out there's some really nice numerical solvers out there that make this nice. I mentioned this, but so the eigenvalues actually turn out to be positive. So for stable crystals. Or in other words, since these are positive, another way of saying that is that this matrix always has to turn out to be positive definite. Why is that? Well, it basically comes from, we had written, I'm not going to write out the whole term because I'm sure I'll get it wrong, but, if I think about these interatomic force constants and these as displacement patterns, what we know is that if this represents sort of a potential energy, what we know is that if the potential energy, so if you don't have a stable crystal structure, then the potential energy would potentially go down if you displaced away from the so-called equilibrium points. So if you have an unstable crystal structure, that basically implies a negative value of one of these eigenvalues, a negative eigenvalue, and a negative eigenvalue implies that if I were to displace my away from equilibrium, I could actually get a lower energy, a lower potential energy, which violates the whole idea of being in equilibrium in the first place. So it turns out those eigenvalues, or the values of omega, they're actually always positive. In fact, a really good way to figure out whether a crystal structure is stable or not using first principles calculation is to actually calculate the phonon spectrum. If you go to calculate the phonon spectrum and you find out that you get phonons that are imaginary, then boom, you know right away that there's something wrong. And it's usually that the crystal structure you've provided is an unstable one. Okay, one more thing. Let me clear the slide and talk about, just again remind you about what these dynamic matrices look like and what the eigenvalue problem looks like.